Okay, well, we might as well get into the lecture. You'll remember that last time we were starting to introduce the notions of hardware caching, how they're designed, how we make these things fast, because remember that we have usually some small number of clocks, maybe tens of clocks, certainly not hundreds of clocks to make decisions about where data is or where to put it and so forth. We just don't have a lot of time. So the hardware caches are typically designed to make some choices automatically so that they'll be really fast. So we had these parameters. Capital B was the block size. Capital S was the number of cache sets. We keep both of these a power of 2 to keep life simple. Now, one of the things that you find interesting is that if you look at Intel processor cache statistics, you'll notice that they have some non-power of 2 number of cache sets. So you definitely run into designs where people don't necessarily follow all of these strictures, but it is very nice for keeping things simple. So capital B, capital S are both powers of 2. We have some number of cache lines per set, which does not need to be a power of 2. And that means that we can take our addresses, the memory access has an address associated with it. We can take that address and map it to these various values very easily. Okay, so the bottom lowercase b bits is going to be the offset within the block, and then the next bits are the cache set, and then the rest of it is the tag. And tags will be distinct within cache sets. Yes, was there a question?
Could you explain what a cache line is again?
A cache line is basically the block of data that the cache is holding, plus whatever bookkeeping information the cache needs to keep as well. Okay, so the cache line will contain a valid bit to say, yes, there's some data in this cache line. It'll contain the tag as well, saying which block it is that's in the cache line. Okay, any other questions? All right, so that's that. We talked about this stuff. So this is basically pictorially what I was just saying. So we have the block offset, which is always the bottom lowercase b bits, because capital B is 2 to the lowercase b, so that's why we can do this. Capital S is 2 to the lowercase s, and so we can easily map that out. And then the tag is going to be the top remaining bits. Okay, so the within a cache set, a particular tag will always be unique, but across cache sets you may see the same tag used, and that's perfectly fine. Everything works fine with that, because it's a combination of the tag and set index that has to be distinct. Okay, and we talked about direct map caches. Remember, this is one where we have some number of cache sets. Each cache set only contains one line, and this was because it's really easy to tell if we have our line or not if we can only hold one line in each cache set, because you just look at the tag in the line and the tag of the access being performed and see if they match. And if they don't match, we know that this block is not in the cache. Okay, so this is great, super easy to implement, at least as far as caching is concerned. Hardware caching certainly does have its challenges, but it is easy to implement in the logic. We have a very small amount of logic we need. But we talked about the specter of conflict misses as well. And conflict misses are pretty hideous, because you can have a program that's otherwise performing wonderfully, leveraging its caches, it's got good locality of access, and then it happens to get a particular stride where everything goes into one cache set or a small number of cache sets, and suddenly the cache appears to be much smaller than it actually is. That's disastrous, because now we no longer get the benefit of our cache, even if we have a reasonably regular access pattern. Okay, so that was the issue with direct map caches. Then we had fully associative caches, which only have the one cache set, so we don't have any bits that we have to devote to set indexes. But you can see now that the tag is humongous. Okay, so we have one set and everything's in there. Conflict misses go away because we only have one cache set. So the whole cache is contained in the one cache set. You can't have any pattern of accesses that makes this cache look artificially small. But the problem is we have these large tags. A block could be in any cache line, so I have to look at all of them, and the logic for doing that quickly is going to be large and involved. Okay? And then I also have a lot of tag bits to examine as well because I don't have any bits devoted to a cache set number. Okay, so you can see that fully associative caches are great, but they're also complicated, and so we don't usually do this. And we sort of left off last time saying, well, wouldn't it be great if we could blend these two things in some way? And it is an accurate observation to note that these are extremes on a spectrum. And so somewhere in the middle is this world of set associative caches, where basically you apply both techniques. You have more than one cache set, and each cache set has more than one cache line. So that makes life a lot nicer. You basically dramatically reduce the chance for conflict misses, because if you think about how programs typically work, a program might only be reading from at most 3 or 4 different areas of memory when it's doing its computations. Remember our vector add? We're reading A, we're reading B, we're writing the result. So maybe you have 2 or 3 or 4 different memory regions you're accessing or manipulating when the algorithm is running, but you're probably not going to have many more than that. So you could imagine that having 4 lines per set or 8 lines per set and having a large number of cache sets could dramatically reduce the possibility of having conflict misses. That's been the observation, and it's worked really well in practice. Okay. So here is a 2-way set associative cache, just because I don't want to draw complicated slide pictures. Typically we call it E-way set associative cache, where E, remember, is the number of lines per set. So this would be an example of a 2-way set associative cache. And remember, you can have 3-way, 5-way. It's not really, like E can be anything really, depending on the design you want to achieve. But normally it's a power of 2 just because. Just for reasons, I guess. You'll also notice here that even though we say it's a 2-way set associative cache, we still have 4 cache sets. So part of specifying what a set associative cache is, you would say this is a E-way set associative cache with this many cache sets and this block size. And that fully specifies the details of the cache. Okay, so M-bit address, you can see that we break it apart like this. Since we have 4 cache sets, we have 2 bits devoted to identifying the set index. We have B bits for the block offset, and then the rest of it is tag. Okay? And so we can use the set index to identify the cache set that becomes active, and then within that cache set, we look at all the cache lines to see which one has the tag that is appropriate for that address. Okay? So not bad, right? We've figured out a way of blending these two approaches that works pretty well. Okay? So 4-way set associative caches are very common. 8-way are less common, but still pretty dang common. And then anything higher than that, you probably won't see. Because at that point, the cost of the logic, designing that logic, doesn't really buy you anything really significant. Because like I said, you typically notice that program behavior is constrained to access like 4 or 5 areas of memory at a time. And then maybe that's about it. Okay, so where does this concept of associative come from when you're talking about a set associative cache or a fully associative cache? Remember that we have some number of lines per set. And we need to look up which line we need to access based on a tag, which is a key. And so this is very much like a dictionary where you say, I have a key and I need to look up the thing. That key isn't really a location. It's a value. Okay? And so this is an associative memory. And so this is where this notion of an associative cache comes from, because we're associating a line with a particular key. Okay? So that's the reason for that name. It's not really any more fancy than that. I just wanted to spell that out so that you know. Okay? Any questions? Alrighty, so that's that. Yeah, so the key, like I say here, is a concatenation of the tag plus the valid flag. It's kind of a neat thing because since you don't care for looking up a cache line with a valid bit of 0, why even look at the tag in that case? So In that context, the valid bit can sort of be stuck into the tag for the cache line, and then the logic can just look at all of it at once. So that keeps it nice and simple. All right, yeah, I think I kind of really beat that one to death, but there you go. 3 slides on the simple concept of what it means to be a set associative cache. Now, we talked about reading. That's pretty much all we've talked about so far. And there were some questions last time about writing, and they were good questions, but they were before the time. So we're going to start talking about writing to caches now. We need to think about how writing would interact with the caches. Because, again, you can come across multiple strategies for dealing with writes, and we could do things in a really good way, a nice, fast way, which maybe is more complicated, or we could do this in a horrendous way that makes things really slow. If I write to a word and it's already in the cache, that's kind of the easiest circumstance. We call that a write hit because the block's already in the cache. I can go ahead and update the block. But then I have something to think about because so far we haven't discussed any machinery for making sure that that data that gets cached and is now changed makes it back to the next level of memory that is being cached. So we have to think about how to handle this thing. First option is write through. It's called write through because when that write hits the cache could say, oh, I don't know how to deal with writes, and it could turn around and just perform that write back to the next level of the hierarchy. Okay? So every write to the cache causes the cache to write the entire block back to memory. Do we like this approach? Seems wasteful, right? Because if, we have a program that is exhibiting spatial locality, then if they write to a location, it's a good assumption that they'll probably write to something nearby soon. Think about our vector sum program, or vector addition. Or temporal locality. I'm accumulating something into a particular memory location. So if I write to a memory location, I'm probably going to write to that one again. Why would I not apply caching to those operations as well? So write through is kind of unappealing. We're going to be incurring the costs of accessing the next level of memory all the time. Okay? So every single write would be incurring that cost. So a second approach requires our caches to become a little bit more intelligent. If we add a dirty flag to our cache lines, then we can keep track of the fact that the block contains data that's in the cache but hasn't yet made it back to the next level of memory. Okay? So that's called write back. Eventually, we will write that block back to the next level. But we're not writing through. We're not keeping the next level in sync all the time. Okay? You can see, as I say in the slide, that the point where we write that dirty data back to the next level of the memory hierarchy is when we evict the line, because that's sort of the last possible moment that we can do it. Any earlier, and we're kind of wasting time, because there may be more subsequent writes to that block. So it makes sense to do it when the line is actually evicted. So now we can actually support locality of writes. Programs everywhere are jumping up and down for joy because now they'll be faster. Writes to adjacent values are likely to hit the cache blocks, and obviously temporal locality, if I write to the same value multiple times, it'll still be in a block that's probably in cache, so we'll be really happy. And the block, when it's evicted, then we'll go ahead and take care of that write. So the next level in the memory hierarchy will see less traffic, and that's always good because that's going to improve our performance. Okay? Drawback, there is a drawback. We need more transistors. And so we have more logic. It's going to be slightly slower, but hey, probably the trade-off in cost of propagation delays and increased complexity of logic is going to more than pay off because we're not going to be talking to this next level of memory, which is going to be significantly slower. Okay, questions? Yes.
Would this be one of the reasons why computers and phones and so on ask for us to wait before shutting it off sometimes, so they can do this transfer?
That's a good question. Is this the reason why a lot of devices want us to shut them down cleanly? This is a very limited example. I don't want to say no, because it is possible that this level of the caching mechanism could be affected by that. But typically where you see the real need to shut things down cleanly is between DRAM and persistent storage. That's the pair of levels where things go catastrophically wrong if you don't shut things down cleanly. The file system implementation in the OS will have a lot of data cached. Like we're talking megabytes and megabytes of data. And so it needs to make sure all of that is flushed down to the persistent storage before the system is turned off. And so that's like, and it's the same thing with mobile devices because you'll have DRAM and then you'll have flash memory, which as we discussed is still way faster than a spinning, crazy mechanical device, but it's still slower than DRAM, and so there's reasons to have caching there. And so in both of those contexts, the fact that you are accumulating dirty data is really important to resolve before shutdown. But at this level, where we're talking about hardware caches, it's less crucial, if I'm going to be so bold as to say that. I know that's probably a more complete answer than you wanted, but I believe that's correct. Okay, any other questions? All right, let's see. So let's say that we also have the situation where somebody writes to something without actually having read it first. And if you think about our vector summation or our vector add, I have to say vector add because that's more accurate. Vector add is a great example of that because I allocate result and then I take A and B and I sum them into result. A and B, sum them into result. And because of that, I will be writing to things that haven't necessarily been cached yet. And so that's called a write miss because we have a cache miss on a write operation. And so again, we have a couple of choices. We could write allocate where basically when somebody tries to write and the block isn't in the cache, then the cache turns around and reads the entire block that was being written to into the cache. So you can see that this is an assumption, right? That the program's going to perform subsequent writes. It's going to exhibit good spatial and or temporal locality. So that's a nice assumption, but then again, this is complicated. So the cache has to be more clever to do write allocate. We could also do no write allocate, where if a write miss occurs, we're just like, okay, we're going to get out of the way and let the write go through and hit the next level of memory. Okay? Again, this is going to not allow us to cache up write. So if the program is exhibiting good locality, no write allocate is going to be sad. We're going to probably lose some time. Okay? So typically write back caches will do write allocate because why not? It makes all kinds of sense to do so. And write through caches, so really simple caches, are also not going to handle this additional complexity. Okay, so there's a few details about how these caches handle write. Any questions? All right, so there you go. There's some details on that. We're going to talk about performance modeling of caches. And we used to spend a lot more time and energy on this, but right now, the way that we really explore this is to give you a really high-level sketch, and then that'll be about the extent of our discussion. Although, if you do cache analysis, like actual either simulation or you run a program on a processor that includes benchmarking capabilities, which, like, Intel's processors are so crazy smart, it blows my mind. But you can definitely get performance metrics out of the processor that will tell you how many cache misses did you have at this level and so forth. So it's pretty amazing. But so we're going to talk about the most basic ideas, and then we're not really going to expect you to do any highly detailed analysis because it's just not worth the trouble. And you're going to get into that world of the swag, right? Hopefully everybody's familiar with that term, the scientific wild-ass guess. And why waste the time when you can run the program and make a measurement instead? And that will actually be useful. Okay? So anyway, we have this notion of a miss rate, which is basically my program is performing accesses. Some percentage of those are misses. So the miss rate is just a value between 0 and 1 telling you what percentage were misses. Okay? Hit rate is easy to understand as well. That's just the percentage of the accesses that are hits, and so there should be a relationship between the hit rate and miss rate that we all understand. Then you have this is where it gets even more hand-wavy, because at least hit rate and miss rate you can measure and understand what they mean. Hit time is what is the cost of accessing a value that actually is cached. Okay. Now you'll notice that I say here it includes all necessary steps for delivering the value. So we have to select the cache set, we have to find the line in the set, we have to pull the value out of the block in the line, and so forth. Okay. But what have I not told you? Well, what if it's a write? What if it's a read? We haven't talked about any of that. Okay, so you can see that we're sort of really simplifying this down to a single number. How many clocks does it take to serve a hit out of the cache? Then we have the miss penalty, which gets even more approximate. Okay, so again, we have all the business of saying, hey, what cache set would it be in? Let's look at all the cache lines. Oh no, it's not in any of the cache lines. Now I have to go and access the next level of the memory hierarchy. Okay, so we do that. We pull a block of data from the next level. But what if we also had a dirty block that we have to evict? So now we have to evict that as well. That's also all encapsulated in this miss penalty. So you can see already that this is a pretty gymongous approximation. Okay? So suspend your disbelief. That's kind of necessary in these discussions. So we sort of say the hit time is going to be one nice, simple, clean number, and the miss penalty is going to be another nice, simple, clean number, when it really kind of isn't. Okay, so but it does illustrate exactly how valuable caching, and good cache-friendly, or there's another interesting approach to designing algorithms, which I may mention at some point. But let's say that we have a simple case where the hit time is 1 clock. Yay, that's super fast. I mean, most of the time you don't see that even on L1 anymore because processors are super fast. Miss penalty is 100 clocks. Okay, so if we had all reads from the cache, we'd have 1 clock. Now we know that's not going to happen because we have compulsory misses where we have to get data into the cache. That's why we don't like to measure performance right away. We like to let it reach a steady state. But let's say we had a hit rate of 80%. How would we calculate this? Well, this is why I love being at Caltech, because if I were somewhere else, like at the art studio, people would be like, I don't know. But let's say you have a hit rate of 80%. Well, it'd be 80% times 1 clock and 20% times 100 clocks. And then you get your average time. So you get about 20 clocks, 21 clocks per access. Everybody got that? So let me ask you this question, the more important question. Is a hit rate of 80% good? Well, what about a hit rate of 90%? Is that good? So you can do the math. And you end up with, oh, well, that's a lot better. We're around 11 clocks per access. And you look at your memory costs when you access them, and you think, okay, the next level of the hierarchy is 100 clocks. 11 clocks is definitely a lot better than 100 clocks. But 11 clocks isn't all that great when it comes to 1 clock. And so you say, well, what about 95%? Maybe 95% is really good. And you do the math again, and you end up with about 6 clocks. Okay? So it's pretty good. But hopefully you can see why when you design an algorithm or you design a program and you want it to be cache friendly, you're shooting for like 98, 99% hit rates. You don't want 95% hit rates because you're still leaving some performance on the table at that point. Okay? Maybe that is the best that you can do for a particular design, but you'd really like it to be a lot better because that's where you start seeing a real performance improvement, where you start to see accesses at the performance level of the cache, not at the next level behind it. Okay, any questions about that? If you read research papers about cache-friendly algorithms, which there's a ton out there because everybody cares about this kind of thing, then you'll see them shooting for very high hit rates, if they possibly can. 95% is meh level hit rates. Okay? So, we need to have our programs think carefully about caching so that we can leverage these caches really well. You'll get a lot of exercise thinking about that next assignment. I am sorry. I kind of feel like sorry, not sorry, but I am still kind of sorry because it's not my favorite assignment. But yeah, the compiler needs to think about this as well. But you can see that cache designers also they're in a real challenging situation because they have to figure out how to make this cache as fast as possible and also as useful as possible so that we can bring up hit rates. What's the easiest way to bring up hit rates? Make the cache bigger. What happens when we make the cache bigger? Physics. Oh, physics. So we have a problem there. And so if we increase our cache size, we're probably going to increase our hit times. There's going to be an automatic cost associated with that. Okay? Increase the number of lines or the size of each line, but then our memory gets larger and we run into difficulty. Okay? We could try increasing the block size and keep the rest of the cache constant. The idea being that if we have a program that's accessing a particular region of memory, then more of it will be brought into the cache and we'll get better performance, at least for the way that the program's behaving. But then remember, we're bringing a giant chunk of data from the next level and our miss penalty goes up. So our hit time could go down, but our miss penalty will go up. What if we increase the number of lines per set? Well, hopefully I've blathered on enough about this that you recognize immediately what would happen if you increase the number of lines per set. You have all that logic that has to look at all the tags and see which line has the tag that we're looking for. Well, now that logic gets more complicated when we have a larger number of lines per set. Okay? So that's probably going to increase the hit time. Also, when we have more lines, we have a larger choice to make when we evict somebody. And so the eviction logic gets more complicated. So that's probably going to increase the miss penalty. Okay? So this is annoying. It's just like, what the hell do I do? Direct map caches are super simple. Maybe you could increase the cache size with the direct map cache. And that might help because typically when you have a direct map cache, when you increase its size, you're increasing the number of sets because each set only has one line. And so that's probably going to reduce the likelihood of conflict misses. But you're going to run into that program that generates a ton of conflict misses, and then that programmer is going to be pissed. So you always have those kinds of situations that you run into with direct map caches. Okay? So you can see that this is really difficult. So what do processor designers do? They simulate a lot and they run typical program workloads and they try to see how well or how badly a particular cache design will work. And then they just try to pick something based on measurements that does pretty well. Okay? So that tends to be what they have to do. But you can see how challenging it is to try to design one of these. Okay? Any questions? Good, because I've never designed a cache, and I don't have any answers. But and that's why you don't have to do something like that on the exam. Now, we've been talking about data caching. Again, we didn't talk about writes. Well, writes are important. Also, we have instructions and data, and instruction reading in particular will typically have good locality. If you have a reasonable program that's just running linearly through its instructions, everybody likes that. So the processor typically will have multiple memories, multiple caches that it's using for different purposes. Everybody remember the Harvard architecture? You see it peek through here again because we have a separate instruction memory and data memory now. Okay? Obviously, like I was saying, overall the abstraction that we have in these systems is a von Neumann architecture, but you can see how within the processor there's a lot of benefits to having the instruction and data memories separate. Okay? So, we have typically this kind of layout, and like I say here on the slide, typically this will be abbreviated iCache, Dcache. One of the things that you'll get in assignment 5 is a little program I wrote because you might ask the question, well, how do I know what my block size is, or how do I know what caches I have? Well, it turns out you can ask the processor because the Intel processor is freaking brilliant. And so there's an instruction that you can execute on the processor and say, hey, tell me what your caches are. And it'll say, okay, give me some memory and I'll do that. And so I wrote a little program that you get to run on your computers to figure out what your caches are, and it'll tell you all of these details. Okay? So you can find out the block transfer size and so forth. Yes?
You start doing naughty stuff and writing two instructions, that's like flush the instruction.
Yeah, so what does happen when you write two instructions?
I mean, there's like the OS protection, right?
Yeah, well, so there is OS level protection, but even if you're doing something fancy like just-in-time compilation. Just-in-time compilation is sort of a real challenging thing for security. You have to design just-in-time compilation to be secure if you're going to be nice about it. But you can certainly be insecure about it, and then you can execute whatever you want. So that's definitely a possibility. Typically what happens on these processors is that if you perform a write close enough to the instruction pointer, the processor just doesn't even care. Like, it's not going to invalidate the instruction cache. It's just going to execute the instructions that are in the instruction cache. So that has historically been the behavior of Intel processors. And I know that because of my interest in computer viruses when I was a kid. Because there were viruses that would have really tight loops, and they would write to instruction memory, and then, but what you didn't realize is that the cached instructions were still the old values, and so there's some really clever techniques. Thankfully, nobody's insane enough to do that in the real world. I also don't know if that behavior has changed over time. Like, it really depends on the processor itself, like what processor architecture you're talking about. I'm sorry, which model number you're talking about, like how close you can get to the instruction pointer without it being observable. And it may be that at some point people started doing something more clever with keeping the instruction cache up to date, but nobody thinks self-modifying code is a good idea. It's just a terrible idea. And so typically the instruction cache can assume that once it has the instructions cached, it's okay. All right, any other questions? All right. I don't even know why I show you this. I don't know if anybody even has a Core 2 processor anymore. But I'm showing it to you because I have examples in the slides, so I'm going to let you see what's going on here. Okay, so we have 8-way set associative caches in the Core 2 processor. You can see that the L1 caches are both 32 kilobytes, and then the L2 cache is going to be several megabytes. Now, remember that the instruction and data caches are separate, and then L2 is unified. What that means is that you're caching both instructions and data in this one cache. Okay, that's all we really mean. Block size all the way through is 64 bytes. If you have a, and typically what you run into on these processors is that when you have multiple cores, then they're divided up into pairs of cores which share an L2. And so they'll have their own L1 caches, and then they'll have a shared L2. Pairs of processors will have a shared L2. And then if there's any other levels of caches, they'll be shared across all the cores. Okay? So anyway, you can see here, like I say, small number of cache lines per set, but large number of cache sets. So that is intended to keep the logic relatively simple. And because we have a small number of lines per set, I mean, 8 is plenty. Like I was telling you, most programs will only be touching a few areas of memory at once, concurrently. So 8-way set associative is more than sufficient to keep from getting into horrible trouble. Okay? You really have to try to behave badly anymore. Okay, Core i7. This is going to be much more like what we have nowadays. Somebody will have like an i-series processor. And you can see again that L1 is still 32 kilobytes. Now we have a second level of caching between the small caches and the bigger cache. You can see the L3 cache is unified, 8 megabytes. But then we have this L2 cache, which is 256 kilobytes that sits in between. Okay? Those are all 8-way set associative, except for the L3, which is 16-way set associative, and so forth. Okay. We would expect, let's just think about what we expect. Because remember, the scientific process is all about saying, I have a theory about what's going to happen, and then we take measurements and see if our theory is true. Okay, or a hypothesis. I really should use the term correctly. So we have these 3 levels of caching on the I-series processors. We'd expect that the degradation of performance would be smoother if programs are behaving badly as far as caching is concerned. The the Core 2 series processors, since they only have 2 levels of caching, we'd expect to have a much more dramatic drop-off in the performance as programs behave more badly as far as caching is concerned. Okay? So let's think about what kind of program we could write to measure cache performance. Let's have the program allocate a chunk of memory of size elements. You could say that this is going to be size bytes, but we can also say it's size words, whatever the element size. Because remember that typically we care about stride at the level of the word size. Okay, so we allocate an array of size elements to scan through. And then we access the array with stride k reference patterns. Okay, so maybe we grab 10 kilobytes, and then we do stride 1, and then we do stride 2, and stride 3. And then we allocate 20 kilobytes, and we do stride 1, and stride 2, and stride 3, all the way up. Okay? And so forth. The question is, how do we expect this program's performance to behave as we vary both size and stride? For example, if the size fits entirely within the L1 cache of the processor, does it matter what stride we have? The answer should be no, because regardless of stride, we're going to be accessing data that's still in L1. We get a lot of temporal locality in this case. We're talking at a high level of granularity. We get a lot of temporal locality because we're accessing the same values again, and they're still in L1 because L1, the working set is entirely inside L1. What if it doesn't fit entirely in L1? Will the stride start to make a difference? Yeah, like big time, right? So we have these expectations about how this program might behave given our understanding of caches. Okay? So there's 2 different kinds of locality. We have spatial locality, where we access data items that are close to other data items that hopefully were brought in because they were part of the same block. And then we have temporal locality, where we access the same thing more than once. Okay? Any questions? This is the setup. All right, so what you can do is run this program. And, so we already talked about a lot of this stuff. If the working set and stride are small, we're going to fit entirely in L1. But really, who cares about the stride if the working set is small? Okay? When the working set doesn't fit completely within L1, but it fits in L2, well, if we have stride 1, we're going to get maybe a miss on the first axis in the block. And so we'll see the L2 performance. Because remember, we said this working set will fit entirely in L2, so we should see the L2 performance on that first axis. And then every subsequent axis will be in the same block, so we'll see L1 performance. So we'll see one axis that's L2 and the rest of them are L1, and then one that's L2 and the rest are L1. If we have a larger stride, well then we'll start having fewer L1 axes and more L2 axes and so forth. You should start seeing a degradation in the performance until you get to a certain stride, and you should expect to just see the L2 performance. Everybody got that? Okay, so we've increased our working set. And so you can do the same thing throughout these various axes as we vary the size and the stride. Okay? You can draw a pretty picture. Oh, I love pretty pictures. Okay? Is anybody interested in running this on their own computer, by the way? No. Okay, maybe one person is maybe 2 people. Everybody's like, meh. So this is a program that's actually available off of the website associated with the textbook, including the Excel spreadsheet that makes this pretty picture. So not hard to run. I actually generated all these pictures myself. And you may remember, if you got the textbook or ever looked it up on Amazon, it's got a picture like this on the front of the book. Every edition has, and they've gotten better and better because processors have gotten better. Okay, so here we have the 3D surface showing our caches. And I will tell you one thing. With 3 levels of caching, this stuff is complicated. And with speculative prefetching, this stuff is complicated. So there's a lot of features on here that I can't explain readily. You probably won't be able to explain them readily either. You may have some guesses, and I will have some guesses. But it's kind of an interesting thing that as the processors have gotten more sophisticated, and this mountain has gotten smoother and smoother, there's fewer cliffs on it. I'll even show you a picture of that. It becomes harder to predict exactly why various things are occurring. There's some interesting issues here. Okay. So let's see if we can figure out our picture. So the size is on the bottom right. You can see it starts closer to the back, being a small working set size, and then we increase the working set size as we come forward toward you. And so you can see that for very small working sets that fit entirely within L1, stride is irrelevant. Stride is the one going from left to right. You can see that we have stride 1, stride 3, stride all the way up to 32, stride 32 reference pattern. So it doesn't matter as long as our working set fits in L1. Okay. Oh, and also, of course, the vertical axis is the read throughput, so megabytes per second. You can see that we're topping out at like 6.5 gigs per second, at least in this program on this hardware. I think that's my laptop. I don't remember 100%, but I'm pretty sure this is my laptop. I just don't even remember. Okay, so we increase stride and you decrease spatial locality. What you start seeing is misses at the level that you'd love to be in, but you see hits at the next level because your working set is still fitting within that next level of cache. And so, for example, you'll notice like this sort of central plateau in the yellow that's labeled L3. So that would be the L3 performance, but you see a slope down from the L2 performance to the L3 performance. So that's why you sort of see that plateau on the left between 4,000 and 5,000 megabytes per second. That whole thing is probably going to be just about L2 cache performance. And then it slowly tapers down to L3 cache performance as you have more and more of your accesses being an L2 miss and an L3 hit. Okay? Pretty wild. Now here's another picture. Look how stark that picture is. This is my old laptop. It's currently sitting in a pile of random debris in my office because I don't have anything else to do with it. Okay. Can't install the latest OS X on it or anything. So, but you can see that this has only 2 levels of caching, and you can see how starkly different the system behaves at these different levels. Okay, so you've got an L2 cache. You have L1 as long as your stride is small or your working set is small. You see only the L1 performance, but then you get this pretty sharp tapering down to L2 performance. And then you just get this giant precipitous drop-off to main memory performance from L2 as the working set gets too large to fit in L2. Okay? Everybody got that? Pretty exciting, huh? I like seeing this stuff. It's like, ooh, the engine. The engine sucks. Write your programs intelligently to avoid the sucky regions of this picture. That's kind of the giant object lesson today. Now, yeah, so this is what I was already talking about. You see a really sharp decline because, and this is the reason why the I-series processors have a 3rd level of caching, because we'd like to not have this. We'd like to smooth this out as much as possible. I mean, honestly, we'd like all of it to be great, but we can't because of reality. And so we try to make this as smooth a degradation as possible. And I mean, if you think about it, if you run your program with one configuration and you run it in another one and it's slightly slower, most people won't whine about that. But if you run it in one way and then another way and it's like 5 times slower, people will be pissed. And so you'd like your processor to kind of smooth that out if you possibly can. Okay, let's see. There's this weird dip toward the back, and people always notice this, and they're like, what the hell is going on there? Well, at some point, your working set is so small that you have the loop setup and loop teardown, and you have the function invocation to go call the test loop and the return from that, and all of that stuff has an overhead as well, and it starts to overwhelm the measurements. it starts to look really horrible because you have a very small number of accesses over which to average that stuff. So that's why the data stops being trustworthy behind the curtain. I should just throw it out. I mean, it's just kind of outlier data you should throw it. Yes?
Is there a way to minimize that kind of overhead?
That's a good question. I don't know if there is a way to minimize the overhead. The problem is the way that you minimize the effects of overhead in most performance benchmarks is scale up the number of tests you're doing so that your average approaches the accurate value, if you possibly can. The problem is if you're going to do something like this, then you start having to think about, well, how's my branch prediction going to affect, this stuff? Because you're going to have loops. And if you have loops, then you're going to have comparisons and conditional jumps. And if you have conditional jumps and comparisons, you're going to start having branch prediction misses and hits start to affect the timing. So I don't know. I mean, I think it's probably possible, but I just haven't thought about it enough to know specifically how one would do that. Now it's interesting too because this is like the version of the program from 1 or 2 editions of the book ago. It could be that the most recent edition of the book has an updated program that one could use as well. So that would definitely be an interesting thing to look at, but I just haven't investigated it in enough depth. Okay, any other questions? All right. Yeah, it is weird that you have such a big effect. You also see this weird bump. It's like, why in the world is there a bump over here? Well, if you think about it, you have a stride that's going to basically just miss each cache line. But you get to a point where you're taking large enough strides, and you're going to make it through your entire working set and get back to the beginning, and if the cache is smart, it's going to still have that block around. And so you might actually see a little improvement in the hit rate when you get to a certain stride. It's weird, but there. Okay? So that one's interesting. You can see that there's sort of like no man's land where you definitely don't want to be, because that's just going to be horrible. Okay? Here's the other thing. Yes, question?
Sorry, could you explain that again? I don't think... So you go over...
Yeah, so the idea is, for example, if you have a 64-byte block, and this was on 32-bit... No, I think they were also 64-bit processors, but that's kind of immaterial. So you have a 64-byte block, and let's say you're accessing the first word at the beginning of each one of those blocks. So your stride is only hitting each block once. Well, then you're going to go through all your blocks, and then you're going to go back to your beginning, and all of the blocks that you accessed earlier are going to have been flushed out because you continue accessing those things. Well, if you have a stride that's large enough, let's say that now you're accessing the end word in one block, and then you can skip a block and access the first word in the next block, well, then that block that you completely skipped doesn't get loaded at all. And so that allows you to keep around some of the blocks from a previous iteration because you haven't needed to load other interstitial blocks at all. And so you can see them. You get a little increase in temporal locality in those weird situations. I would never want to depend on behavior like this. Okay, any other questions? Okay, so another thing to notice, this is why that laptop is my previous laptop and not my current laptop. Notice its throughput is like 820-ish megabytes per second. The last diagrams that I was showing you for this one are like 6 gigs, 7 gigs throughput per second. Okay, so you can see that the motherboard chipset and the memory modules, the timing of the memory modules, all of that stuff has an effect on your memory system, the performance of your memory system. And so if you're designing a computer, like you love gaming or something like that, then you want to design a computer that maximizes the performance of all these different subsystems. Okay, here's a Core 2 Quad. So same processor now. 4 cores instead of 2 cores. This was another machine that I had in my office before its power supply burned out. And you can see that it was achieving over 7 gigs per second throughput. Same horrible drop-offs, because the processor still has the same caches on it, but the memory system was more performant. Okay? Okay, there you go. So cache is king. basically, since we have this horrible performance gap between the processor and memory, caches are the solution. They basically let us have large memories that are as performant as small memories as long as our programs are well written. Okay? We've got to keep our cache hit rate up to get that. And so you can see that it's really important to think about this when you're designing data structures and so forth. Like I said, you write JavaScript code, you write Java code, you write Python code. You don't get to think about these kinds of things because there's an interpreter or something else sitting between you, your code, and the processor. So sadly, you don't get to think about these fun problems. But you write in C or C++ or D or Rust or any of those kinds of languages, or assembly language if your life really sucks, then think about this stuff a lot. It's really important. Okay? And you can take a really slow data structure, a slow algorithm, as you will do in assignment 5, and you can make it blisteringly fast just by thinking carefully. Okay? I'm going to take a few minutes. Don't hate me, but I'm going to take a few minutes to introduce the next topic. You may have noticed that processor performance has kind of, let's say at least as measured by clock speeds, has stabilized for various reasons. And so there's a couple of approaches that people have chosen. One is to make the processor more intelligent itself. We parallelize the instruction execution. We do prediction, which is a terrible idea, evidently. We can't keep our data safe anymore. Okay. So this has allowed processors to continue to become more powerful, even though you've seen CPU speeds staying in the 1 to 3 gigahertz range. And they have been for like 15 years now. Like I've been looking, and they're pretty stable. So another approach is to just dump more cores onto the processor. And it's like every year I ask this, who's got a cell phone with multiple cores in it? It's like everybody's hand goes up because everybody's got like a dual core or quad core processor on their phone, on their computers, on their toaster, their microwave oven, everything else. Okay? We still have the same issue though, that the memory is a lot slower than the processor. So what we're going to talk about next is what happens when you introduce multi-core into this issue of caching. And so I think I'm just going to wrap it up there because I want you all to like me. What we'll do next time is start talking about how you deal with caching in the context of multi-core. So I will see you next time.